Dear students, let's continue our practice on Mathematical Analysis 1. So, the next topic is limits of functions. Let's begin with the definition of limits of functions. So, here we have formal definition with epsilon and delta. So, let a function fx be defined in some neighborhood of a point A, including or excluding this point. A number A is called the limit of f of x as x tends to A, and we denote by limit x tends to A, f of x is equal to A. If for any arbitrarily small number epsilon positive, there exists the corresponding number delta, which is depends on epsilon greater than 0, such that the inequality implies x minus a less than delta implies the next inequality, f of x minus a less than epsilon. In this case, we call number a the limit of f of x when x tends to a. So this is formal definition of limit of function. Now, example, prove that the first one, prove that limit x tends to 3x squared is 9. And in this case, how can we prove this equation, this limit, sorry? So, limit x tends to 3, x squared is 9. So, let's use the formal definition. For any epsilon greater than 0, there exists delta depends on epsilon such that x minus, instead of a, we have 3 now, because x tends to 3 and capital A, it is 9. So x minus 3, it's less than delta, and it implies to f of x. Instead of f of x, we have x squared now. X squared minus 9 less than epsilon. So we need to prove this inequality now. And obviously, we can factorize this inequality. How? The left side, I mean. This is x minus 3 and times x plus 3, and this is less than epsilon. However, x minus 3 is less than delta. Yeah. So we can continue this. We can continue from this place. Like so, we can put instead of x minus 3 delta. So, or we can factorize here. Here you can see also x minus 3. We can open this one. It means x minus 3 less than delta. It means minus delta. It is bigger than x minus 3 and less than delta. Without absolute value, of course, because here now we open the absolute value. So, and then what do we get here? We have x minus 3 move to the left side. Our inequality, double inequality we have here. 3 minus delta is less than x, and it is less than 3 plus delta. 3 plus delta. So, and now we can write here x plus 3 also. So in this case, if we add the 3 to both sides of our inequalities, we have the following double inequality: x plus 3 in the middle. This is 6 minus delta and 6 plus delta. We get this inequality. And now, what we get here? We have this one. So, if you continue this one, x minus 3, it is delta from our inequality. And x plus 3, it is less than 6 plus delta. So, you can rewrite this inequality with red as x minus 3, it is less than, so this is x minus 3 times x plus 3, absolute value of course, less than, now here we have 3, this is delta, this is just delta, it is less than just delta, this one. This is less than 6 plus delta, times 6 plus delta. And all of them is less than epsilon. So now we can find here delta and delta with epsilon. We need to find delta because from our definition we need to find this delta. There exists delta. That's why we have to find it. Here we get inequality depending on delta in this case. Delta and epsilon. With epsilon it should be. So if we solve this inequality, we get the answer. Epsilon here just any. We can consider just any number here which is positive. And here just inequality. We have quadratic inequality. So it is just x and 6 plus x less than delta. And after solving this quadratic inequality, we get the answers which delta 1 is 3 minus 9 minus epsilon, and delta 2 is with method of intervals we can solve this inequality. It's very easy. Delta 2 is so 9 plus epsilon minus 3, and we have 2 delta, and it will be enough to say that delta is equal to delta 2 because delta 2 it is less than delta 1. Delta 2 it is less than delta 1. That's why we can take just delta 2 as delta. So this is proving the limit of the function with definition. So now next one. We have two special cases. The first one is f of x tends to 0 as x tends to a, and f of x tends to infinity as x tends to a. If f of x, limit of f of x, x tends to a is equal to 0, in this case we call f of x is infinitesimal function. Okay, now so here we have the next definitions, and here we have examples of infinitesimal function. For example, x squared tends to 0 as x tends to 0, or x, this one, for example, x cubed minus e tends to 0 as x tends to 2. If you put 2 here, this is 0. So this is limit. It means just putting the value which x tends to this value instead of x. So now we can continue here, and we have one-sided limits also. So what it means, one-sided limits, we have left-sided and right-sided limits. So in this case we have the definitions of left-sided and right-sided limit. So we call this right-sided limit if we can take the neighborhood of x from the right side. When we calculate the left side limit, we take neighborhood of x, left the neighborhood of x, and we can calculate this limit. In this case, we will denote right side limit as limit when x tends to a plus 0. This is last side, right side limit f of x. This is right sided. Here is plus 0. This is right side limit. And limit x tends to a minus 0 f of x is a. This is left side limit. Left sided limit. So, and it means, again, one more time, we need to take the when we calculate right side limit, we need to take right sided neighborhood of x. And if we calculate left sided, we need to take left sided neighborhood of x. From this definition, we have x minus a less than delta. Yeah? So in this case. So now, let's. And here the important theorem. F of x has the limit at point A if and only if there exist one-sided limits as x tends to A which are equal to each other. So we need to satisfy this equality. This ones should be equal, and then it's equal to A if left-sided limits and right-sided limits are equal. They are exist and they are equal. In this case, we have limit. Only in this case. And we call this is limit of function. Now, example. Here we have some example. Find the limit of a function f of x at the point x is 2. Here, consider one-sided limits of f of x, left side and right side. Let's begin with left-sided limit. We can see here in denominator we have x squared minus 3x plus 2. We can factorize it, x minus 1, x minus 2. And in denominator we have the absolute value function. So this function we can factorize again as x minus 2 and x minus 4. But, however, we calculate the left side limit. So the first expression x minus 2 should be negative because this is 2 minus 0. This is left neighborhood of 2. Here we have 2 minus delta 2 plus delta. So we need to consider this part now. In this part the absolute value is negative because it's less than 0 we get. So that's why we put here minus and open absolute value is minus. The other one is non-negative here. And the answer, when we put x instead of x2, we have minus 1 over 2. And when we calculate the right side limit, here we have both of them are positive because x minus 2 here and the 2 plus we get, yeah? So in this 2 plus it is just this part now. So in this part this is positive, the right side. In the right side neighborhood, this function, this expression x minus 2 is positive, absolute value x minus 2. That's why this is just 1 over 2 we get. Okay, next example. Find the limit of the function, this one. So, here we have this function f of x 1 over 1 plus 5x minus 2. At the point x2, we need to calculate the limit. So, first let's consider again one-sided limits. This is, so, limit, here, x 2 minus 0 firstly, 2 minus 0, and now f of x, this one, 1 over 1 plus 5x minus 2, the power it is. So, and let's consider the left side limit. So, left sided limit here, if you put here 2 minus 0, it means this is tends to 0, and the fraction tends to infinity, but this is tends to minus infinity because it's not 0. This is just we can say minus infinity we get because it is left side neighborhood of 2. That's why we get just 1 plus 5 minus infinity power, and 5 minus infinity power it tends to 0. It tends to 0. That's why it is 1 plus 0 just, or 1, or just 1. So now the next one, if we consider the right side limit, we have 1 over, and now we have just plus infinity, 5 plus infinity. So it tends to 5, the degree of plus infinity tends to infinity because this is goes to infinity. So 1 plus infinity, and it goes to 0. It goes to 0. Okay, we have some properties here. These properties we consider it in limit of numerical sequences also. So now let's continue. So now we have the most important limits here. So the first one is limit sine x tends to 0, sine x over x. This is 1. This is first important limit. And the next one is this first one. The second one is limit x tends to 0, 1 plus x, the power of 1 over x. This is number E. If you remember, we considered in numerical seconds also the same one, but with natural numbers here. And we have corollaries of this second one. Limit 1 plus, we can change it like limit x tends to infinity, 1 plus 1 over x, the power of x. So it is also number E. The easy way of remembering is it should be 0 here, yes. 1 plus 0, it is 1. 1 over 0, it is infinity. 1, the power of infinity, it should be. Here also the same. 1 plus x tends to infinity here. That's why this is 0. And this is infinity again. 1, the power of infinity. And this is equals to infinity, E, number E. So, and we have the next corollaries of the second important limit. We will do when we're doing practice problems. We will be using these corollaries also. So now, okay, next. Next one, here we have some examples. So, practice problems now. Let's start with the number 1 here. Evaluate the limits. Limit x tends to 1, x squared plus x minus 3 over x squared plus 1. So, here, what should we do? This is just very easy limit, just putting instead of 1, there is no problem here. Instead of 1, if you put, instead of x, if you put 1, we have 1 squared plus 1 minus 3 over 1 squared plus 1. So, there is no problem. Here we have just 1 plus 1, 2, 2 minus 3, it is minus 1 over 2. The answer is minus 1 over 2. This is very easy one. And now, let's consider the next one. So, for example, here, this one, number 7. Limit, this is also not so hard to understand. 1 over x squared. It is, when x tends to 0, it tends to 0, the denominator. 1 over 0, it is infinity. Very easy. So the next one, number 8 for example, or number 10. Let's do number 10. So limit x tends to plus infinity, x squared minus 5x plus 1 over 3x plus 7. So in this case we have just we will consider the powers of terms, and the greatest power here is 2. So, and the x squared here, you can see the numerator is greater than denominator. I mean, power of numerator is greater than denominator. So that's why the numerator goes to infinity faster than denominator. We can continue just like dividing x squared, or just write here plus infinity, because this is obviously I said so. However, the power of the numerator is greater than power of denominator, it goes to infinity. If we have inverse example, for example, if the power of denominator is greater than power of numerator, then we have 0. Now, next one, number 3, evaluate the limits. Indeterminate form 0 over 0. What it means, indeterminate form 0 over 0. First example, for example, limit x tends to 2, x squared minus 5x plus 6 over x squared minus 4. So, why we call indeterminate form? Because if we put 2 here, we have 2 squared. Let's calculate it. 2 squared minus 5 times 2 plus 6 over 2 squared minus 4. Here we have 0 because 4 plus 6 minus 10. This is 0 and this is also 0 over 0. That's why we call it indeterminate form 0 over 0. You cannot calculate in this case, but we can simplify this expression and then calculate the limit. So, and we will denote by like this 0 over 0. It means indeterminate form 0 over 0. Now, let's simplify this expression. Limit x tends to 2. Here, x minus 2, x plus 2 using the short multiplication formulas. And the numerator is factorizing to x 2 and 3 here. X minus 2, x minus 3. And now, we can cancel the x minus 2 and x minus 2. And we have here x minus 3 over x plus 2. And we don't have any indeterminate form here because when we put 2 instead of x, we have 2 minus 3 is minus 1, 2 plus 2 it is 4. So minus 1 over 4 the answer. So in this way we can do indeterminate forms only by simplifying and factorizing. So next one. For example here, which one? Let's consider number 9 here. Limit x tends to 0, 7th degree plus 5x6 plus 4x cubed over x 7th plus 2x cubed. So here the degrees of the the highest degrees are equal, 7 and 7 in the numerator and denominator. So we can write here answer 1 because if you remember from numerical limit of numerical sequences, when x tends to, so we can take here just ratio of coefficients of highest terms. Here we can take ratio 1 and 1 here. That's why 1. Or just doing like dividing by x the power of 7 numerator and denominator, and then we get the answer. Limit x tends to 0. Here we have 1 plus 5 over x plus 4 over x, which degree? 4th degree, over here we have 1 again, and plus 2 over x 4th degree again. So now when x tends to 0, it tends to infinity, and this is also tends to infinity, and this is also tends to infinity. Or doing easier our work, we can divide by x the least power also, x the power of 3, for example. There is no difference between them. For example, here we can divide by x3 also, and then we can get, for example, we'll not get here infinities, we get here zeros. So here we have now we have the other ones. For example, if we divide by x the power of 3, here we have x fourth plus 5 so here we have 5x cube, yes, and plus 4. And here we have x 7, it is x fourths plus 2 here we have. And the answer is, so here is 0. That's why we need to take the ratio of coefficients with least powers, with term with least powers, the ratio of coefficients with least powers. Here it's just 4 over 2, it is 2. We can see here also it stands to 0, it stands to 0, it stands to 0, and we have 4 over 2 just. The answer is 4 over 2. Okay, now let's consider the next example. So for example, number 12 here. Limit x tends to 1, 3, 1 minus x cubed plus 1 over x minus 1. If you put 1, we have again indeterminate form 0 over 0 here. And that's why we need to find by simplifying and factorization of this expression. So the common denominator is here 1 minus x cubed. We can write like 3, 1 minus x, 1 squared plus x squared. And here we can take as minus, can change the places, 1 minus x, and we have minus in the middle. So, and now let's continue. So the common denominator is this one, and the limit x tends to 1. So now here we have this one, and the 3, 1 plus x squared. 3 minus 1 minus x squared. And now so by the expression, so 1 minus x, 1 squared plus x squared. So here we have 2x. If we take out the minus x squared plus x and minus 2 here. So now let's continue. So this is equals to so here we can take out this minus also, doing x minus 1, changing places, and cancel the two minuses, and we have just limit. Let me write here one more time. Limit x tends to 1. So now we can cancel the minuses. X squared plus x minus 2 over here we have just x minus 1 now, and x squared plus x plus 1. So now let's consider the numerator, and here we can factorize as x tends to 1, x minus 1 and x plus 2, because the roots of this polynomial is 2, minus 2 and 1. So the denominator is x minus 1, x squared plus x plus 1. So we can cancel them, and then we don't have any determinant form in this example. So just putting 1 instead of x, and we have 3 over 1 plus 1 plus 1. 3 over 3. Or the answer is 1. So this is the answer of our example. The limit is equal to 1. Okay, now let's consider the next ones. So number 15, let's do. Here we have limit x tends to 6 and x minus 2 minus 2 over x minus 6. So let's continue. And here, if we put 6, it is 4 minus 2, it is 2. 2 minus 2 is 0. And 6 minus 6, it's also 0. So we have the indeterminate form 0 over 0. And now, how to solve this example? Here we need to multiply here the conjugation form of this expression, or in other words, here limit x tends to 6, x minus 2 minus 2, x minus 2 plus 2, this one, and divide by it, x minus 2 plus 2 times x minus 6. Okay, now, and now, what we get here, so, and now, when we open this one, it is limit x tends to 6, x minus 2, and minus 4, over, here we have x minus 6 times x minus 2 plus 2. So, x minus 2 minus 4, it is x minus 6. X minus 6. And this one is also x minus 6. And if we cancel them, then we don't have any indeterminate form after the canceling these two ones. And now, just putting x instead of x6, we have 1 over 6 minus 2, it is 4. The square root of 4, it is 2. 2 plus 2, it is 4. The answer is 1 over 4. Okay, let's continue. And now, so, here we have more examples on indeterminate form 0 over 0. And now, indeterminate form infinity over infinity. The second one, for example, limit x tends to infinity, x plus 1 squared, 2 minus 7x squared over 2x minus 1 fourth degree. So here, indeterminate form infinity over infinity. Why? Because if you put infinity here, we have infinity and infinity, infinity over infinity. But how can we calculate this limit? To calculate this limit, we need to consider, in this case, now the ratio of coefficients of terms with highest powers, highest degrees. In this case, the highest degree is 4, because here we have x fourth degree, the highest one, and here we have x squared times x squared. It is also gives fourth degree. That's why let's consider just coefficients of these fourth degree terms, x fourth. So the coefficient of x fourth is here 1 times 49, yeah, 7 squared, and here is 2 the fourth degree, it is 16. So the answer is 49 over 16 just. One more time. We can open these brackets and multiply these terms and divide by the highest term and then find the limit also, we can do it. But the easy way is just find the only when x tends to infinity. When x tends to 0 with least powers. When x tends to infinity, we can just find the coefficients of terms with highest powers, and we need to take the ratio of these ones. If it is in fraction form, of course. Okay, so now next one is number 9, for example. Here, limit x tends to infinity, cosine x over square root of x. So when x tends to infinity, the cosine x so when x tends to infinity, the cosine x is, we need to use here equivalency, or so here we have the forms. I want to show you the other ones also. I think I need to put the equivalency. Okay, let's continue this example. Just continue. Okay, so here cosine x when x tends to 0. However, the cosine function is bounded function, it tends to 1. That's why it is, the answer is here just 1 over infinity or just 0. So the next examples. And now, if we have the indeterminate form infinity minus infinity, we need to multiply by, for example, this 5 number 1, limit x tends to infinity, square root of x squared minus 1, and minus x squared plus 1. Here, if you remember from numerical limit of numerical sequences, we did such kind of examples. So we need to multiply by conjugation form and divide by it. So x squared minus 1 plus x squared plus 1 over this one, x squared minus 1 plus x squared, this one, x squared plus 1. And then we have here just a squared minus b squared, the formula a squared minus b squared. So here we have x minus 1 minus x squared minus 1 minus x squared plus 1. Or now here this one, this brackets, let's denote by bracket. So and when we open, they are cancelled, and we have just minus 1 minus 1 minus 2. And we can calculate limit x tends to infinity minus 2 over the expression here, this brackets. And this is goes to infinity, because here you have infinity plus infinity plus infinity, this is infinity, but infinity minus infinity, this is indeterminate form, infinity minus infinity. So in this case we have just minus infinity answer. Now let's start the next example. Okay, using the fundamental limit, sine a over a, evaluate this limit. You can call just important limit or fundamental limit. So now let's consider limit, first one, limit x tends to 0, sine 3x over x. Sine 3x over x. So this is to solve, to find this limit, we use this first fundamental limit. Let's remember again. Limit x tends to 0, sine x over x, it is 1. Here, what we have? We have this fundamental limit, but some with little differences. Here we have 3x. So we can do this example in form limit x tends to 0, sine kx over kx, it is k. This is k. So sine kx over kx, this is k. And here we need to do this kx, so times 3 here, multiply by 3 and divide by it, or right here. So 3 over 3, we don't change our example, but we do our fundamental limit. So now this is 1. This is 1, but we have k here. But we have k here. So 3 times 1, it goes to 1, and the answer is 3. It goes to 1, and answer is 3. The answer is k, but this once it goes to 1. This limit is goes to 1, but the answer is, it will be k just. If you have here kx. If you write in sine kx over x, this is k, yes. Okay, now next example. For example, here, for example, number 3, limit x tends to 0, x cotangent 5x is, so now times here. So to find this limit, let's write in this form. X times cotangent x, it is cosine 5x over sine 5x. And now, what do we get here? When x tends to 0, cosine 5x tends to 0. This is cosine 0, and this is 1. 5x tends to 0 because this is tends to 1. And now we have this one, x over sine 5x. So there is no difference. Here we have limit x tends to 0. Now x over sine 5x. One more time doing the same work as previous one. Times 5 over 5. And then we have just now 1 over 5. 1 over 5. Okay, now the next one. Which one? Let's consider. Let's show one example from this second fundamental limit. For example, here, number 2. Limit x tends to infinity, x minus 1 over x plus 3, x plus 2, the power of x plus 2. So how can we find here the limit using the second fundamental limit? So limit x tends to infinity. So let's doing the integer part of this fraction. So dividing these two expressions, polynomials, and we have x plus 3 minus 4, x plus 3, x plus 2, and then x times infinity, x tends to infinity. Here we have x minus 1. So x plus 3 and x plus 3 gives us 1. 1 minus 4, x plus 3. The power of x plus 2. Now, it should be the same with the power. That's why you write like limit x. We can do this in the middle plus and do here minus, because in the form is plus. We have x tends to infinity. So 1 plus 1 over x plus 3 over minus 4. The power of x plus 2 times x plus 3 over minus 4 times minus 4 over x plus 3. So this one's with this one gives us number e. So there gives number e, and then we have just, if we continue this, equals to e the power of limit x tends to infinity, e the power of these two ones now. So let's multiply minus 4 x plus 2 over x plus 3. And when x tends to infinity, this fraction tends to minus 4. And that's why the answer is e to the power of minus 4. Okay, now the next one more example here. For example, let's consider with this one, number 17, for example. Limit x tends to infinity, x times natural logarithm 2 plus x minus natural logarithm x. So now limit x tends to infinity, x times this one we can write as the division of these two logarithms, natural logarithm, I mean two expressions, 2 plus x over x we have, and then it means natural logarithm 2 plus x over x, the power of x, it goes to the power. Yes? So now let's find the limit of this one now when x tends to 0. And how to find it? It is, look here, we can divide. We can divide by terms. So it is limit x tends to infinity, natural logarithm. So here 1 plus 2 over x times the power of x. So now this is so we can divide by 2 here. One plus x 1 over 1 x over 2 times here x over 2 times 2, and we have just x here, multiply and dividing by 2, and this one gives us what? Number e squared it is. So the answer is natural logarithm e squared, or just 2. So by the same way, we can do with when x tends to 0 also. When x tends to 0. For example, number 18, this is with the same way we can do it. So it was the last example for today. The next time we will continue the topic limit of functions, and we'll consider other the corollaries of the second fundamental limits and continuity and other topics. Thank you for your attention.